Welcome back to our second video in Unit 6. As a quick recap, we are trying to create an interval of values, say from A to B, where we are some percent confident that P, the parameter for the population proportion, is inside that interval. We could just say P hat is our best estimate of P and just leave it at that. But we know that if we were to take another sample from the population, we would get a different P hat. And then would we say that our best estimate of P is that P hat or the first one? That's not good enough. So by creating an interval of values, we can say with a high degree of confidence that P is somewhere in there. And that's going to be the best that we can do. So we set up some things that will help us calculate how this interval works. And we first had to come up with a model to use. And we're going to be using the sampling distribution of P hat, so the sampling distribution of a sample proportion. And we talked in the last video about how even if we don't know what P is, which is the whole point here, if we meet the same conditions that we talked about before with the sampling distribution of P hat, we can say that the sampling distribution is normal in shape with a mean of P hat, which is our best estimate of P, and then a standard deviation that looks the same as it did before. We're just plugging in P hats because we don't know P. So let's take a look at this distribution. This is normal. The distribution is normal, so let's draw that curve. Right. Based on our sample that we took, we're still talking about our original example, the proportion of US adults that went on vacation in a past year. Our mean of this distribution is P hat. That's our best estimate of P. So P hat is right in the middle. And we are trying to construct an interval of values that we are some percent confident that P is inside. This is the sampling distribution of sample proportions for that population. So if P hat is our best estimate of P, then it would make sense that our interval, whatever these values are that are on the ends, that confidence interval is going to be centered at P hat. It will always be centered at P hat. This will always be the very middle of the confidence interval. So if you think about it, we're going to be going some distance to the left to get the low point of the interval, and we're going to be going the same distance to the right to find the upper end point of the interval. So let's look at what that would be. So let's say we want a 95% confidence interval. We want to create an interval from A to B such that we are 95% confident that P is in that interval. And as we just said, the lower endpoint of that interval is going to be to the left of P hat, and the right endpoint is going to be to the right of P hat, and they are going to be the same distance apart because we want P hat, our best estimate of P, to be right in the middle of that interval. If we want to be 95% confident that P is inside that interval, that is equivalent to saying, I want A and B to be the numbers such that, I did a bad job there, sorry. I want A and B to be the numbers such that the area under the sampling distribution curve in between A and B is 95%. That's what that means, right? Because that means that 95% of the time, P is going to be in this interval. Only 5% of the time would it be outside. Okay, so we know that A is just as far away from P hat as B is, and we know that this area is 95%. So how do we find what these numbers are? Well, this should be reminiscent of a type of problem that we've talked about in the past. If we know the area between two values, and we want to know what these values are, that's when we use like the inverse norm function on our calculator, right? Inv-norm. That is going to be what we do here. But instead of talking about what the endpoints of the interval are, it might be more helpful to see what it looks like when we standardize this normal distribution. Because right now, this curve has a mean of p hat and a standard deviation that's not particularly easy to look at. Oh, that's the standard error. See, I messed that up too. It's the standard error because it's got p hats in it. So instead of this mean and this standard error, let's standardize it to the standard normal distribution and see how this changes when we look at it that way. Just to repeat myself, what we were looking at here is we want to know what the values of A and B are, such that 95% of the area under the curve is between A and B. If we standardize, the mean of this normal distribution, instead of p hat, becomes 0. The standard error becomes the standard deviation, which is 1. And what happens to A and B? Well, remember, when we standardize, at this point, all the values on this axis represent z-scores, right? So we don't know what the value of z is that we need here, but I'm going to call it, and it's not my idea, this is very standard in statistics, we're going to call this z star. This is the z-score that we're interested in, that will correspond to how far away B is from p hat, the center of the interval. Okay? And this is a z-score. It is. That's what it represents. It's z star because it's specifically helping us calculate this confidence interval. This is the notation we use, right? So this is z star. And then over here on the left side, we know that z star is just as far away from 0 as this one is. So this would be negative z star. So all we have to do to find what z star is determine, well, 95% of the curve is between negative z star and z star. If you've got a fancy new graphing calculator, you could go to inverse norm, go to area 0.95, center, and it will give you the values of negative z star and z star. If you've got an older school calculator, you'll still need to go to inverse norm, but you'll need to put in how much area is to the left of z star. This is the one we're going to be interested in. Okay? How much area is to the left of z star? Let's just go ahead and do that. Well, 95% gets us to here. How much more area is left to the left of z star? 2.5%, right? The normal curve is symmetric about its mean, and these have to add up to 5% because the whole area under the curve is 1. So to find z star, we would just do inverse norm of 0.975. Okay? And you could do this on a newer calculator as well. You could just do area 0.975 to the left. And that will give you z star. And it turns out that's 1.96. 1.96. And that would make negative z star negative 1.96. How does that help us? So we know that z star is 1.96. Remember that z-scores in the past, when we first introduced them, that meant that this value, if we were to unstandardize and go back into the regular units, that this value, whatever it corresponds to here, is 1.96 standard deviations above the mean. It's largely the same interpretation here, except remember we're talking about standard errors now. So if z star is 1.96, then that means that B is 1.96 standard errors above p hat. And then, by extension, A would be 1.96 standard errors below p hat. So that's the interpretation we take away from that. If z star is 1.96, then that tells us that A and B are 1.96 standard errors away from p hat. Is there something magical about 1.96? Remember, the z-star value depends on what this percentage is. And this percentage is what percent confidence you want to be that p is in the interval. There's nothing magical about 95%. You could change this number. If this number goes up to, say, 99%, how's that going to change z-star? If this percentage goes up, then you have to be including more area, right? That's going to push z-star further out. That's going to make z-star bigger. If you want to be more confident that p is in your interval is going to have to get bigger, your z-stars are going to have to get bigger, and that means that a and b are more standard errors away from p hat. If you reduce this number to, say, you only want to be 80% confident, well, that will allow the z-stars to get smaller. That will allow your confidence interval to be narrower. Okay? So you have a smaller interval that you're confident p is in there, but as a result, your confidence goes down to 80%. So this is what we're talking about with our confidence intervals. These z-star values depend on the percent confidence. For 95% confidence, z-star is 1.96. The higher your confidence, the higher z-star has to be. The lower your confidence, the lower your z-star has to be. Okay, we are very close to being able to come up with the formula for our confidence interval, our one sample z interval. But before we do that, we were just talking about how z-star relates to percent confidence. I want to see if you can find out what the z-star value would be if we only wanted 90% confidence. What would that z-star be if you only needed 90% confidence? If you're absolutely sure what you need to do and you just grab your calculator, I'll push back a little bit and suggest that you draw a curve like this, because it's really obvious right now, potentially, what you need to do to get this, but in the days, weeks, months ahead, it might become less and less clear. If you want to go back and look at your notes and have that help you, just writing the answer here is not going to do that. Draw your curve. How does this change if we want 90% confidence? Okay. So if you want to do it on your own, pause the video now. If we want 90% confidence, we want 0 in the middle. I'm just going to go straight to the standardized version. Z-star is going to be over here. 90% confidence means we only want 90% of the area inside here. So with a newfangled calculator, inverse norm, center, 90%. We'll give you both of these. You want the positive one. If you've got an older one, you need all the area to the left. So you need 90% plus whatever this is. This is going to be 5%, right? Because these have to be the same. And all of these have to add up to 1. So you would do inverse norm of 95%. That's all the area to the left of Z star. And that's going to give you 1.645. Now, if you remember when we first talked about z-scores, I said that the convention is to round z-scores to 2 decimal places. But you'll see here, I put 3 decimal places. I'll just tell you right now, the most commonly used confidence percentages are 95% and 90%. So the Z star values of 1.96 for 95% and 1.645 for a 90% confidence interval, those are going to be ones that you can probably remember. You might not have to go through drawing the curve and using inverse norm. That's not to say they're the only ones. I could make that any value, but the most common ones are 90 and 95%. If you round this to 1.65, when we get around to calculating the actual interval, what these numbers are, rounding this to 1.65 could have a large effect because you're rounding up quite a bit there. So in general, z-scores are rounded to two decimal places. For most z-stars, for most confidence percentages, 2 decimals is going to be fine. But if you can remember, for a 90% confidence interval, this is 1.645. If you can remember to keep it at 3 decimal places, that will make your life much, much easier. Because I can tell you right now, that is what is the standard for many statisticians. They'll actually take that out to 3 decimal places. Okay, so you should be able to calculate z-star for any percent confidence. If I wanted to know what z-star was for 70% confidence or 99.5% confidence, you should be able to use a sketch of the normal curve and inverse norm to find z-star. Okay. Why are these confidence percentages so high? Well, if we're going to go through the effort of making this interval, we want to be pretty confident that p is inside. We could make a 20% confidence interval, I suppose. But if you're only 20% confident that p is inside, it's more likely that it's outside. What's the point of that, right? We want these confidences to be high. That is going to make our intervals fairly wide in general, but we usually would err on the side of we want to be confident that p is in the interval. Okay, so that's why these percentages are usually so high. Now we know how many standard errors we need to go out on each side in order to get a certain percent confidence area in the middle. So I want to generalize again. We will calculate the confidence interval for the example that we started the unit with. We are going to do that. This is going to be in general. All right. So if we unstandardize, we're going back to the original sampling distribution. It has a mean of p hat. And we want our interval. I'm aware this is not perfectly symmetric. Just bear with me. This is not to scale. Okay. Say we want a C% confidence that p is inside the interval. Okay. This could be any number. We've dealt with it being 95, with it being 90. Okay. We could find z star no matter what this number is. Okay. Now, we know that this value here, the end point, the upper end point of our interval that we used to call b, actually represents the fact that we are z star standard errors away from p. And if we're on this side, it means we're z star standard errors above p. So this value is z star times the standard error of p hat, which is this here. So this is z star times p hat 1 minus p hat over n. But it's p hat plus that value, right? This is p hat, and we're adding on z star standard errors. I hope that makes sense. Okay, so if this is 95%, then z star is 1.96. So this would be 1.96 standard errors above p hat. Okay, the lower value of our interval is going to be the same as the upper one, except instead of adding z star standard errors, we're subtracting them. So we have here p hat, the sample proportion, minus z star times the standard error. And again, the z star value depends on whatever the confidence level is. If c is 95, then a 95% confidence interval, z star is going to be 1.96. If c is a 90%, then z star is going to be 1.645. So, we finally have all the pieces we need. We can construct this interval knowing just 3 things. P hat, n, and the confidence level we desire. Those are the only things we need. We don't need to know anything about the population to calculate that interval. We just need the sample proportion, the sample size, and the confidence level we're interested in. I know I've said this before, but it bears repeating that it's not very helpful if you take a sample from a population and you want to estimate the population proportion to just say, well, my best guess of the population proportion is what we got in the sample proportion, p hat. That is true, but it is not a very good estimate, because if you were to take another sample, you would just get another p hat that's probably different. And then you would say that that's the best estimate of p. And it's just not very good because you're not confident about it. So if we want to estimate what p is, it is better to say, hey, here's an interval of values within which we're pretty confident p is in there. That's what we're doing with these intervals, right? So by giving ourselves a margin of error of z star times the standard error of the sampling distribution on either side of p hat, that's what we're doing here. We're subtracting z star times the standard error here. We're adding z star times the standard error here. By giving ourselves that margin of error, then we can say that we are 95% or 80% or 99.5% or whatever, C% confident that p is within the one sample z interval of this. And there are two different ways of writing it. The first one here, our confidence interval is always centered at p hat, for now anyway. And we're either adding or subtracting z star times this, which, remember, this is the standard error of the sampling distribution of p hat. Okay? So we could also write it this way, p hat plus or minus z star times the standard error of p hat. Okay, you'll see it written both ways. This one is more helpful if we're comparing a one sample z interval to different types of confidence intervals that we're going to talk about later. This one is actually what you would use to plug in your numbers, right? And remember, all you need to calculate this interval is p hat, the sample proportion, n, your sample size, and the percent confidence that you need, which will tell you what z star is. Okay? I've written it both ways. On the AP formula sheet, it does not show these. What it does say is something similar. So on the formula sheet that you'll have access to during the AP test, and any test that you take in this class, as long as I remember to give it to you, which if I don't, please remind me. I want to make sure you have the access to the formula sheet. It says confidence interval is statistic plus or minus critical value times standard error of statistic. And you can see what that looks like using this format. The statistic, in this case, for a one sample z interval, is p hat. Plus or minus, the critical value is what we call z star. And the standard error of the statistic is the standard error of p hat, which is equal to the square root of p hat times 1 minus p hat over n. Okay, so we are going to be talking about two sample z intervals, one sample t intervals, two sample t intervals. The formulas will change, but the basic structure of how the confidence interval is calculated will be the same. It'll be some statistic plus or minus some critical value, is z star or t star. We'll talk about that. And then, or there's even another one, we'll get to that. And then times the standard error of the statistic, which will always be the standard error of the sampling distribution, which we've already talked about for proportions and means. So, I know that I said we'd get to calculating this interval. We didn't quite get there today, but now we know what the formula for the confidence interval looks like. So we should be able to, in the next video, actually calculate the confidence interval for the US adults going on vacation in that previous year. So I hope you're excited for that, to finally figure out what that confidence interval is. We're going to talk about how to do that and what it means. How do we interpret it? What does it mean if the confidence interval goes from A to B? How do we interpret that? So we'll talk about that in the next video, and we'll see you there. Take care.